It's my physics class. What did I say in the last one? 60. It's a hard one. Yeah, I haven't been studying very much.
It's really interesting that Havoc courses over in engineering. So it's something very much more. Yes, I don't know.
Who's teaching it? Clara.
Yeah, really. I don't think we have to say
Nobody. Nobody.
If I make a break, I'll probably not do that. Or helping them like, well, like I know we're not that, like, a lot of money, and it's just like, what if it's done, then I'm not gonna be.
Yeah. Where do you want to go? Where do you want to go?
You said Davis.
Oh, that's it.
I went there. To Vista. It was so cool. I'll be studying.
One of my friends, Davis, is studying there right now. We're getting a degree.
San Francisco,
It's so
yeah.
interesting. One of my other friends was Davis. She's getting a degree in
All right, where is everybody? Question, I think it's a holiday. So, I want to start today, so we're going to, if you want to talk about atomic absorption today, I want to take a few minutes to make sure we go over the class again a little bit, of additions, which we haven't really gone through in numerous detail here, but I think we talked about it in sections. And I want to hand the quizzes back. Okay, so what am I showing here?
The part that makes it turn into.
That's true, and what is that called?
Wait, the whole thing?
The sample goes into the valve, and oxygen fuel from the sides, it hits the glass bead and aerosols, and the particles will travel through.
Okay, so
So it draws up the smallest particles so they can get rid of.
okay.
Yeah.
So I'm gonna get rid of this now. So, for this to occur, we're essentially measuring, say we'll take a metal, and for this to occur, what state does this metal have to be in? Free? What is free atom? Free atom, right? It has to be a free atom, right? And how do we start with our sample?
Dilute.
It's aqueous form, right? So how do we get our the sample from here to there?
Heat it.
Okay, and that is called
Atomizer.
nebulizer, right? Okay, it's doing all those things. So we call it a nebulizer. People call it also referred to as essentially a spray chamber, but it's the unit that takes the sample that's coming in from the capillary tube. You all use the instrument this week so far. Is that right?
Yeah.
Okay. So you see the capillary tube. You know you can adjust a little knob right here that essentially opens and closes the orifice diameter. It essentially allows it to aspirate more or less sample liquid. And the aspiration rate, so you can change that. Okay. The sample goes in this example with this one, it hits this glass bead, like you said, and it generates this mist of droplets, liquid droplets. And the mixture of the gases rushing through here, through these baffles that are shaped from like a corkscrew. And they then generate this Venturi effect of sucking the droplets that are in suspension, that are small enough to remain in suspension in the gas that's running through these baffles. And then they come up to the flame. And they have a mixture of this oxidant, which is what in your case?
Air.
Acetylene?
Oh, air.
Both.
What's the oxidant? Okay, air, right? And the fuel is acetylene, right? In some cases, if you wanted to get a higher temperature flame with acetylene, what might you do? This is for some elements.
Pure oxygen.
Okay, that's one way to do it. That's a little bit dangerous. But what you do instead is I'll have some other oxidants. It's more enriched in oxygen than atmospheric oxygen levels, and typically they'll use something like nitrous oxide. So it's not combustible, but it has a higher molar ratio of oxygen, so you can get a greater flame temperature that way. So the whole idea then is to take your liquid sample, right? So you know you have to have a liquid. If you, and some of you will do this, if you wanted to actually measure levels of copper or lead or something in some environmental sample or biological sample that was not a liquid, what would you do?
Dissolve it in acid.
So you have to process it upstream of this to get it into an aqueous form. Right? That's what you have to do. All right, so when the sample is going through here, it's being sort of aerosolized. There's a number of things that the sample, the composition of the sample undergoes in order to enter the flame, right? And so if you have a sample, you have metal in this aqueous form, what's the first thing that has to happen when it's entering that spray chamber in order to start processing it so that it actually can be produced in a form that's free atoms?
Spraying is a little deep.
Is that right?
I don't know if it's the first step, but is it sprayed against that little bead there that aerosolizes it?
Okay, and what is, all right, so it's aerosolized in these droplets, right? So once you have these droplets, but the droplets get transported up into the flame, that's what I'm going to say. So there's a number of things that are happening in the flame. And what is the flame providing to us in your case for the air-settling flame?
Combustion.
Evaporating solvent?
Okay, so the flame
Oh, yeah.
is providing what service for us in terms of turning this?
It's turning the water into gas.
Putting them in their free atom state.
Okay, and it's doing that because it's, what is it? It's providing
Energy.
Energy?
thermal energy, right? It's providing thermal energy. And I'm saying, and it's obvious that providing thermal energy because it's hot, but in other types of instrumentations, the source of energy to take a sample from the liquid into the free atom state is not a flame, but it could be electrothermal energy, right? Or some other source of energy. It's that thermal energy that's being provided by the flame is a relatively inexpensive, simple way to provide a lot of thermal energy that's going to then drive this process of going from the aqueous into the free atom. And that first process the flame is facilitating is to desolvate. We know that all of our metal atoms, presuming that they're in acid in here, right, or they're in some aqueous form of weak acid, that you have metal atoms that are existing either as free atoms in that solution or as metal complexes in that solution that are dissolved, right? Okay. We know, or you know, that if you have particulates of things in here, that could be a problem, right? And we'll talk about why that is. So ideally, you want to have your metal that is dissolved in the aqueous phase within that liquid sample. Okay. And there are a number of problems that occur that are commonly encountered if that's not the case. So you have your metal in here that now exists as either free metal or some complexes with things that are dissolved in that aqueous phase. The first thing you have to do is to, with the flame, is that it's desolving. So it removes the hydration sphere around the metal and the metal complexes. Right? And that takes thermal energy. Right? So you're evaporating that liquid. So you're taking those liquid droplets that are being entrained up into the flame, and you're evaporating the water around the metal, the hydration sphere, so that you can generate, at that point, desolvated metal complexes. Right? And now they're desolvated, they're actually up in that early part of the flame, they're existing as a solid, right? Because you desolvated and you have metal and metal complex solids that are now suspended in that flame matrix that they're passing through very quickly. So after you desolvate, then you have to vaporize. And the vaporization is turning that solid up into a gas form. So you desolvate, obviously it's going to remove the water. You vaporize, turning the solid into a gas. The third thing is you volatilize. which you are turning gas phase atoms, atom or complexes, into free atoms. Why do we need to have free atoms in that flame space to interact with the electromagnetic radiation that we're shining?
Because those are the light frequencies that are of interest that we're analyzing, are related to the free metal electronic transitions.
Okay, right. So that's it. So we know that for the absorbance to occur of these incident photons that are of a very specific spectral line, that those photons and the energy associated with those photons are matched exactly with the electron transition from the ground state to a higher excited orbital state of that free atom. And if that metal atom is not free, but instead is complexed, then that changes that energy required to facilitate that excitation, right? And you get a different absorption spectrum. So it's essential that you have the free atoms in that flame space in order to interact with the electromagnetic radiation you're shining through. That's absolutely essential. So we go through these 3 steps in the flame, and it's a relatively inexpensive, rapid way to move from this to this. Are all the atoms of our analyte copper for you now? Are they likely all existing as free copper atoms in that space? Probably not, right? There's probably a significant portion of those atoms that exist in some other state, maybe still complex, because they transit through the flame pretty quickly. Okay? And they're only interrogating with the light as they pass through that light path, which is, in your instrument, is about the diameter of a pencil that's shined across the top of that burner head. And so they're only passing through that light beam for a fraction of a second. And much of it is probably not in a free metal state.
When the metal becomes vaporized, it gets oxidized by the...
Okay, I'll talk about that. You better hope it doesn't, right?
Yeah.
Because why would that be a problem?
It would change the energy states of the free atom.
That's right. So we know that in atomic absorbance, what are we doing? And I was going to talk about this, but I'll talk about it now. In atomic absorbance, if this is your metal, we are taking some wavelength of light that matches the electronic transition energy for this element, this atom, and we are interrogating that, and we are then exciting that ground state electron up to a higher energy level by absorbing that incident photon, right? And this energy matches exactly the energy for the electronic transition. That's why it excites it. And what do we measure when we're doing atomic absorption?
How much of the incident light was absorbed?
How much of it is no longer there, right? We're measuring how much is going in and how much is coming out, and that difference is how much is absorbed, right? And of course, we're assuming that absorbance of that incident wavelength is due entirely to this. But of course, we know that's not true. There's other things that are interfering with the passage of that light through the sample to the detector. It could be reflection, a lot of number of things. There could be other components in the sample that are interfering with it, right? But we're assumed it's all due to this. If we have atoms in the flame that get excited because of that thermal energy in the flame, is that a problem?
Yeah.
Independent of this, if a thermal energy from the flame generates some excited atoms, whether it be full loss of electron, like an oxidation, or just an excited transition, is that a problem?
Yeah, because the light is specific to a certain state of copper, right?
Well,
A
Lamp.
lamp, right?
The lamp,
It's specific.
Well, the lamp generates, the wavelength we select is a specific wavelength that has this, obviously, an associated energy level, right? But I would say that it is a problem because the electronic transitions are typically those that are most energetically favorable. And if we're transitioning, if we're exciting those atoms due to thermal energy from the flame or other things, then those are electrons that are already excited that cannot then be excited due to absorption of an incident photon, right? So it essentially becomes atomically silent to us in terms of their absorption potential. So we do not want to generate atoms that are excited in atomic absorption like this, unless they're being excited by the incident electromagnetic radiation that we're doing example. I'll talk a little bit more about it next slide now. So this is kind of a little more detail of a breakdown. So we see this looks exactly like yours, right? And I made a point before saying on this burner head, we had this slot, this whatever that is, a millimeter diameter, that you had that gas mixture come out, and that little thing flips around and lights it for us, right? All automatically, right? Which is very convenient. And then it burns away. And in the flame, if you were to do a cross-section of what that air acetylene flame looks like, you see that the flame contains a number of different zones of thermal gradient. And so this would be the burner head top right there, and then the flame is coming out, and then it starts igniting here. You have these different zones of different temperatures. Right? And depending on what the gas and the oxide and fuel mixture is, determines to a great extent what the temperature of the flame is, and that temperature varies depending on the combustion zone. So if you look at you're using acetylene and air. The temperature in degrees Kelvin is about 24 to 2,700 degrees Kelvin. Okay. So it's pretty hot. If you need an even hotter flame, you might use acetylene nitrous oxide, and it bumps the temperature up by 3 or 4 or 500 degrees K. Right? Some elements, like aluminum, that are relatively refractory, what that means by being refractory is that it takes more thermal energy to drive them from the aqueous state into the free metal state in the gas, right? It takes more energy to essentially volatilize some elements like aluminum, so they're refractory, meaning they're resistant to volatilization. And so they require a different kind of a flame mixture to get into that state so you can actually measure absorbance. Okay, so things are coming out here from your spray chamber, and they're here for just a fraction of a second, and that's the period of time we have to measure them. Right? Now, if you look at the relationship between temperature.
Do we want them hot enough to get them in their free atom state, but not hot enough to excite the electron into it?
That's exactly what this is saying right here. So if you look at the relationship between temperature in the flame and the energy state of the atoms, you can see that looking at examples for cesium and sodium, this is just using the Maxwell-Boltzmann equation, to look at the relationship between the number of atoms. The N1 is the number of atoms whose electrons are in an excited orbital, and N sub 0 is the number of atoms whose electrons are in the ground state. In atomic absorbance, we want all of these atoms ideally to be in what? The excited state or the ground state? What'd you say?
Ground state.
Ground state. Okay, right, it's right, ground state. So you can see that the relationship in the ratio of excited to ground state atoms, which is what these numbers are, that as you increase in temperature, not surprisingly, the number of atoms in the excited state relative to ground state goes up. So here it's about maybe 3 out of 100, right, are in the excited state compared to the ground state. For cesium, roughly 4 out of 1,000 or whatever, 1 out of 1,000, 4 out of 1,000 for sodium. And as the temperature goes up, and we'll see that when we do atomic emission spectroscopy, where we're looking at emission, we are using a argon gas plasma. It generated, the plasma is a superheated gas that's generated from a radio frequency coil to generate temperatures in that plasma of about 8,000 degrees K, right? So twice as high as that. And we're doing that because we exactly want these to be the excited state, because we're measuring the emission photons when those excited electrons fall back down to ground state. Exactly the opposite of what we're doing here. I'll talk about that. So here you can see, as you get hotter, right now the air acetylene is right around here, that we have maybe 1 in 1,000 to 1 in 10,000 of the electrons that are in their excited state. Okay? And if they're in their excited state due to the thermal energy, we can't measure them by absorbance, atomic absorbance. But we can accept that because that's a relatively small proportion of the atoms in the sample that are in that state at those temperatures. But as we increase the temperature, then we're going to reduce the number of atoms that we can actually measure by absorbance. Okay. This shows a relationship for some metals and makes the point that because of that thermal zone, the various thermal zones in the flame, depending on height of the burner head relative to the light beam determines the relative sensitivity. So you know, for us, that you have your burner head like this, and then over here is the, you don't see it, but it's an instrument of light that's shining out and going across the burner head like that, right? And so when they call the burner height, that's the height, it's the distance between a light path beam and the top of the burner head. Burner height. And did Vince and Taylor go through the process of adjusting the burner height and maximizing the sensitivity?
Yeah.
Okay. So for this burner setting, it can rotate and move in one, two, all three directions, right? It can be raised and lowered in the Z-plane. It can be moved back and forward in the, whatever that would be, X-plane, whatever, forward. And it can be rotated this way, right? It doesn't really move this way, but it can be rotated back and forth this way. And the whole idea is that if you look down on the burner head with a slot like this, is you want the light beam, which is probably about as thick as this piece of chalk relative to this, you want the light beam to be perfectly parallel to the top of this burner so that the thermal zone of the flame that it's passing through is equal across the entire burner surface. And you want obviously to be exactly on top of that slot, right? So you rotate this way and up and back, and do that way. And then once that's lined up that way, then once you start the flame and you're aspirating some solution, what they should have done, the TAs, is slowly raise that until this burner head starts to occlude the light beam, and then you get very large absorbances because it's blocking the light beam. And then you start to lower it, and you keep lowering it, and you're watching as you're aspirating your solution with copper in it, and you maximize the absorbance based on that. And what you're doing by doing that is that you're finding that sweet spot in the flame based on the temperature where you're getting maximum volatilization of the copper in your solution. And that's how you optimize, right? So if they didn't do that, if you go today, you should do that. And you can kind of go in, once the flame's on and there's a dial, I'll show which dial it is, and you can raise and lower that, and you can see, is this really optimized? And for copper, it'll be one place, and for lead, it will likely be a different place. Slightly different. So that should be done with every element. Every element is slightly different. And that's what this is meant to show. And as you look at the burner height in centimeters, that's centimeters for local light beams. Okay? And this is absorbance, that they have different optimal zones or burner heights that reflects their different temperatures at which they are optimally volatilized. And that's something that you want to optimize. Okay, so this kind of puts together all the things that you should be able to describe what's happening. You start with your sample, right there. You go through the nebulizer, the spray chamber, right? And it turns that into, by impact on a glass bead, or there's various ways it does it, but it turns your liquid sample into an aerosol of fine droplets of different sizes. Big guys fall out due to gravity. They go down the drain, and I mentioned probably at least 90 to 95% of your liquid sample goes down the drain. You know, in a small proportion, just a few percent actually makes its way up to the flame. Of that part that then enters the flame, then it goes through those sequences that I mentioned here, where it's going to get desolvated, and it's going to get vaporized, and it's going to get volatilized, dissociated, where you're taking your metal complexes that are in a solid state in that flame thermal matrix, and it breaks them up into free atoms and whatever else is there, right? Now for you want these free atoms now to be available to be interrogated by your electromagnetic radiation to excite them and absorb that photon. That's what you're measuring. If you were doing atomic emission spectroscopy, you would be using thermal energy from the plasma to excite your analytes. And then as that excited electrons fall back in the ground state, they'd be releasing a emission photon of a different wavelength that you would measure. And that's when you measure things that way. And of course, if we're doing it by mass spectrometry, where we have to have things that are fully ionized, because they have to have a charge in order to be manipulated through a electromagnetic field, then you would not only excite them, but you provide enough thermal energy to ionize and fully oxidize a given proportion of your analyte atoms, so that they have a charge and can do something. And we'll talk about all three of those as we talk about those different things. Okay, so part of what we've been sort of discussing to some extent is, recognizing that in atomic absorption that we are dealing with, that we're dependent upon free atoms in a ground state that are available to absorb an incident photon of a specific wavelength. And the photons of specific wavelengths or energy levels that these atoms are able to absorb, of course, is entirely dependent upon its electronic structure. And so that's what that says here, right? So here's a really simple energy level diagram for the electronic orbitals for sodium. And this is relatively simple compared to most elements, right? And what we see is that for all these different types of transitions for sodium, only certain ones are really favorable and are allowed. And meaning that there are only certain of these electronic transitions will occur as a result of interrogating with photons of particular wavelengths of light. And which of those transitions occur, of course, is based on just quantum mechanics and selection rules for those transitions, and of course the energy of the light that we're interrogating. And for many elements, the spectra get very complex. So for iron, for example, there's over 2,000 spectral lines for iron. What does that mean when I say a spectral line?
Separate transition, or separate photon energies that's from a different transition.
Maybe over 2,000 different photon measured by the light being measured.
So say it again.
All those separate lines that they're.
Okay, they're all separate lines, but in terms of how it matters to us, to you in the lab, how does that translate into what you would be considering in setting up a method for measuring copper led by atomic absorption?
You would it would absorb and give off energy at a bunch of different wavelengths, but you'd want to find
Okay,
which
so
one
let's
is
separate that. So absorb is what matters, right? We don't want the give off energy side yet. We want just the absorption side, right?
Only the lines matter that come from the ground state, which I don't think are all those in this place.
Well, that's not necessarily true. So in a typical spectrum, which is shown there, we'll get lots of spectral lines across a range of wavelengths that an atom will absorb photons from, right, across those wavelengths. And so they can be relatively complex spectra. And in the case of sodium, there are 170 different spectral lines between 300 and 700 nanometers wavelengths. For iron, there's over 2,000 spectral lines. And what that means is that photons of these discrete wavelengths can be absorbed by iron atoms, right, and electrons excited to a higher energy level. So when we're talking about atomic spectral lines, we're talking about the specific wavelengths of light that can be absorbed by the analyte to excite an electron to a higher energy level. And it can get relatively complex. And so what's the spectral line of interest for you for copper?
For ground state to first excited state.
What's the line?
484. 484 nanometers, something like that?
Yeah, what's the wavelength?
560.
That was 484.
470 something nanometers?
Wasn't it 484?
Is it
What's
the
the
same?
wavelength? Did you
Oh,
set the instrument
482.
Yeah.
For copper?
487.
482.
Is it the same as what we did for
copper.
experiment one?
Again, 3 what? Copper.
So presumably, you set the instrument to a wavelength to measure the absorbance of a wavelength at 324.8 nanometers. And 324.8 nanometers is one of the specific spectral lines at which copper absorbs photons. And you might say, well, copper is pretty close to iron, so I don't know how many spectral lines copper has. Probably well over 1,500. 1,500 different spectral lines, meaning photons of discrete wavelengths that copper can absorb, right? You get excited. Why is it you're using this one? Why this one, not one of those other ones?
Is that one specific to copper?
Plus the.
They're all specific to copper.
Plus
right?
the incident light coming from the lamp is related to that. Or does it have all?
Maybe it's in knowledge.
Well, okay. Here's a quiz question, right? The hollow cathode lamp that you're using is made out of what?
Copper.
Okay. And what kind of spectral lines does that hollow cathode lamp likely generate?
Copper.
Ground state to excited state? Or all?
It generates a lot of them. I don't know. It generates a lot of them, right?
Yeah.
And are all spectral lines created equally?
No.
Maybe Japan.
No, they're not, right? They're not.
Same
Just as you
speed.
can see here, in terms of intensity, the spectral lines for an individual atom vary enormously in terms of how separated they are and how intense they are, right? And what would you want if you were selecting an optimal spectral line to use in measuring absorbance of an analyte like copper? What kind of criteria might you use to select that line?
Really strong.
Okay, you want separate and intense. You want it not so much separate from each other, but that's true, you do want that.
Something that's the most likely to be absorbed by the analyte.
Well, they all
Whereas-
are.
But what higher energy ones might not be.
Well, this is quantum mechanics, right? There's an energy level here that's going to excite an electron in that copper atom.
Yeah.
So there is a probability, there's a statistical probability that that excitation event will occur. That's true, right? And some are more probable than others. But in general, what you would select is you would select a spectral line, a particular wavelength that is intense, a big line, right? Because what does intensity mean in this context?
Most photons.
More photons, right? And why does that matter?
Because you get the most absorbance. There's more absorbance there. The more photons that you can pass through, it's like you get a higher absorbance.
That's right. So you essentially, it helps maximize your signal to noise in the working world. And sort of because you're interrogating your sample with a greater number of photons per unit time, right? And so you're better able to measure more copper atoms there because you have more photons that can interrogate more of those copper atoms. That's absorbed by more of the copper atoms. So that's one. So intensity is one thing you want. And the other thing you want is free of interferences. And when I say interferences, I mean spectral interferences. Because it's not a perfect world of just quantum mechanics in that matrix of the flame where everything is either on or off. There are other things that could partially absorb, but maybe not absorb as effectively at some of those energies, because as those photons are going through, there's interaction with other matter in that matrix of the flame that sometimes diminishes or changes the energy level of those photons. Okay? So you would select an atomic spectral line for your analyte that is intense and ideally free of interferences. Now this you can measure. Now when you turn on your lamp in the instrument and you align the lamp so it's not facing off kilter, but you're really maximizing the transmission. When you align that lamp, you're maximizing the transition of those photons from your lamp into the detector, right? So you do that, and then you see a readout on the instrument. The readout is some arbitrary units of energy, right? Have you seen that? Okay, you should do this today. You should go through the whole process of setting it all up. When you align the lamp, you'll get a readout of energy on the instrument, and what that readout is giving you a relative measure of the number of photons that are striking the detector, right? And so you optimize that. How would you know, as a young analyst, aside from, you could say, let me back up, you could say, well, I've got a couple options. I know there's also a spectral line at 278 and another spectral line at 345. I'm making these up, and so I'm going to set the instrument to that, because I'm going to go to take the path least traveled. And you would likely measure a substantially lower energy level for the current of the lamp at these alternate wavelengths because not as many photons are striking the detector because they're less intense spectral lines. And so you're selecting a spectral line, not just because the TA said use this, but because people determined that this is a relatively intense spectral line that is free from interferences. And you can open up the manual or you can open up the software on the instrument and it will make recommendations for atomic lines to use because people have spent a lot of time figuring this out. Right? So you don't need to figure this out yourself. You just open the book and go. And I'll tell you that that's where this information came from. So you do all this, right? And now you're starting to measure, or be prepared to measure the absorbance of your light by your analyte in the sample. And so I want to kind of now go back and think about when we say the interference thing, that comes in a number of different flavors that actually ends up being somewhat important. So in a spectral line, now remember I mentioned, what's the main advantage of atomic absorption compared to molecular absorption? Did you read this?
You have to do less stuff to the sample, right?
Well, so aside from all that, let's say the main point is that the atomic lines that you're looking at here are extremely narrow, right? That they can be as narrow as, 5/1000ths of a nanometer, right? And in molecular absorbance, when you were doing a wavelength scan, you saw something that looked like that, right? Over the course of 100 nanometers, probably, right? And so it's a very broad absorption line of your copper ligand complex. In comparison to the absorption spectral lines for atomic absorption, they're extremely narrow, right? Very, very narrow. And the advantage of that, of being more narrow, is that it can be more selective for exciting only the copper atoms, in this case, that are going to absorb that incident photon because it matches the quantum of that energy exactly. But there are some deviations of this optimal, really narrow atomic line spectra that we want to be mindful of. Right? Okay, so that's what this is talking about. So for a spectral line, I want to make sure this is sometimes really confusing to people. For a spectral line in atomic absorption, we call it a dark line. Why is that?
Because it's gone when it hits the...
Because it's gone, because it gets absorbed, right? And so if you're looking after the event, it's missing, right? And so when we talk about spectral lines, we're talking